Hi, welcome back. So today we're going to be finishing up our discussion about universality of quantum computing. Last time, if you recall, what we ended up showing is this construction where we can do a sequence of rotations in two-dimensional subspaces and use this in order to be able to implement an arbitrary unitary transformation. I showed you a method for building these based on controlled unitary operations and controlled single qubit unitary operations. And those can be made using a sequence of controlled rotations. So we built all of that machinery up. But what I'd like to be able to do today is show you that we can do all of this with a discrete gate set, not a continuous gate set. And so the reason why this is important is because of the fact that we cannot perform a universal set of fault-tolerant gates, i.e. we can't apply quantum error correction, it turns out, if we have an infinitely big gate set. Similarly, we also run into a problem where if we have to spend bandwidth in order to be able to specify a particular rotation to a quantum computer, then we would need an infinite number of bits in order to specify the gates that we had in our previous set, just because specifying a real number to an infinite number of bits of precision always is going to, well, require an infinite number of bits. So that is basically that. So today we're going to be showing you how to build out a finite set. And this finite set is going to be Hadamard, T-gate, and the controlled NOT operation. So Toffoli is not actually going to be part of our gate set for the first time since the beginning of the course. All right, so the way that we end up doing this is first, we need to be able to show that we can do single qubit operations using the H and T gate. And the way that our argument goes, let's make a new page, 6. All right. The way that our argument goes is that what we're going to want to do is we're going to want to figure out a way of implementing RZ of some angle gamma over here. And this angle gamma, we're going to want this to be an irrational multiple of 2 pi. Or, in other words, we want to make sure that gamma over 2 pi is irrational. And that what that's going to allow us to do is to play this game where we're doing z rotations. Now let's just envision the angles that we end up getting. Because if we do rz n times, this is equal to e to the minus I z theta to the n. Now, because z commutes with itself, you can actually go through the analysis and see that this actually is equal to nz theta. All right? So if we can do an irrational angle rotation, then what we'll end up doing is we'll do the following. We'll make a set of discrete steps, let's say things that will look like this. Okay, that is actually pretty rational, so I apologize. But if we start going back, then we'll find that this walk, because it never repeats itself, what will happen is that it will actually uniformly spread out over the circle as we continue to apply this irrational rotation over and over again. And so what that means is that if we wanted to, say, build this rotation over here, we would just do this enough times until we ended up finding a rotation that's within angle delta equals theta, like the actual theta that you can get, versus theta ideal. Okay? So you stop at some finite value of delta. Now, a fact that you can see in box 4.1 of Nielsen and Schwang, yes, I know, because I look at that box frequently. A fact is that if you have the norm of u minus v is less than or equal to epsilon, you can, where both of these are unitary, then you can use the fact that the norm of u to the n minus v to the n turns out to be less than or equal to n epsilon. What this means is that errors in the amplitude grow linearly. So if you have to apply a gate n times and there's some finite error, like there would be in approximating the rotation that you want by this, we would end up with just getting n times that error. So if we need to apply the gate n times, then it's suffice, and we can tolerate error epsilon in our final wave function, then we would only need to be able to do RZ with error epsilon over n suffices. Okay? Now, also I should note that the construction that we're showing here is a proof of principle. The exact methods that people will end up using in order to be able to implement these approaches actually are scale a lot better than this. So this lecture is going to be showing that in principle you can achieve universality with a finite gate set, in part by approximating these rotations. But in practice, other techniques will be needed. And I'll mention briefly some of these other techniques later on in the lecture. All right, cool. So how do we end up finding this irrational rotation? Well, the irrational rotation that we carry out actually can be built in the following form: T, H, T, H. Okay? Now this, recall that T up to a global phase can be expressed as e to the I pi by 4. And of course, Hadamard, which we've seen to death, but I'll write one more time, is this matrix. So we can go through this, and also using the fact that e to the negative I z pi by 8 turns out is equal to t up to global phase. And the global phase in this case, which is the irrelevant phase factor that we can always include in a calculation, is e to the negative or e to the I pi by 8. Maybe it's a negative. Yeah. Okay. So we have this. Now, recalling the fact that h e to the minus I z pi by 8, h is equal to e to the minus I h z h pi by 2. And here I'm using a property that u e to the a, u equal, or u dagger, is equal to u a. And a proof, in case you've forgotten, this ends up following from Taylor's theorem. So I use that property in order to do this. The next property I use is h zh equals x. So this it can be written as a sequence of two rotations. Z rotation through an angle pi by 4, and then an x rotation through an angle pi by 4. Okay? Now, we can expand these out using the fact that e to the minus I z pi by 8 is equal to cosine pi by 8 minus I sine pi by 8 z. We can use this, and similarly for x, in order to come up with an expression for this rotation angle. Using this and the property that x times y equals I z, and all cyclic combinations thereof, we end up finding that TH is equal to cosine squared pi by 8 minus I cosine pi by 8 times x plus z plus sine pi by 8 y. And this last bit is multiplied through by another factor of sine pi by 8. This is what we just get by substituting in this expression over here, the similar one for that, multiplying it through and using this. We end up getting that. Now, it turns out that we can recognize that this over here actually is of the form p over here times sine theta, where theta in this case is equal to the arc cosine of cosine squared of pi by 8. i.e., what we want to do is we want to be able to convert this over here to the angle that we're interested in. And by the way, just in case you're curious what this isn't in fact a nice special angle. In fact, it's a anti-special angle, and that's the key point by why we're doing it. We want, this is 0, 2, 8, 4, 0, 6, so on and so forth. And all right, cool. So this p over here, we can verify, this is a Hermitian plus unitary operation. So that means that we can think about this rotation as actually its own rotation. This is e to the minus I p theta, where this theta is that angle at the top. Okay, cool. So now what we end up getting is we end up getting a way of implementing a irrational rotation. So if we envision all quantum states as living on a sphere with 0 up here and Hadamard 0 here, 1 down there, we would end up basically doing an irrational angle rotation about this vector over here. I'll call it p hat for the direction corresponding to that. And so this will end up carrying out a rotation about that axis, causing all of these vectors to precess about there through an irrational angle. And the idea is, using this approach that I talked about previously, we're going to want to argue that we can densely tile all possible rotation angles through here and make any rotation we feel like. Now, this doesn't give us Rx and Rz. I'll show you how we can do that later. But first, let's argue that we can end up making any arbitrary rotation angle we want out of this. Okay, so my claim is that for all epsilon greater than 0 and alpha, there exists n such that the norm of e to the negative I p alpha minus e to the negative I n p theta is less than epsilon. Okay, so basically what I'm trying to say is that if we repeat this irrational rotation enough times, we can closely approximate any rotation that we end up feeling like. Okay, great. So how do we end up doing this? First is, okay, proof. Let delta greater than 0 be a desired accuracy that we want to hit. Now what we're going to do is we're going to envision that we end up subdividing the unit circle in rotations from 0 to 2 pi into n bins. Okay, so we're breaking it up over here. And we want to be able to choose n such that for any theta or j times j and theta sub k, where theta sub k is equal to k theta mod 2 pi, i.e. if we end up wrapping around this over here, we end up going back. Okay, so what we'll have is we want to be able to choose this so that theta j minus theta k, which is the corresponding angles at the center of each of those bins over here, this is less than or equal to 2 pi over n in this case, and we want to choose n such that this is less than delta, where delta is our desired accuracy. Okay, so now if we end up choosing this, then delta is bigger than one of these individual bins. And so what this ends up saying is that, okay, because theta j minus theta k, absolute value, is less than delta, but it's also lower bounded, because every single time we end up taking a step, we end up moving by at least theta. So what that means is that the individual distances that we end up getting between each of them have to be lower and upper bounded by delta between two consecutive places. And this says that given that the maximum distance is 2 pi over n, what we know is that at least one of these bins is going to have 2 entries in it. So there exists a bin such that both j and k end up falling inside here, and j and k are not equal to each other. So this is known as the pigeonhole principle. And it says that there exists some bin such that phi sub j and phi sub k, or theta sub k, are both in the bin. And the reason why this ends up holding is because we have all of these individual bins, okay? And we've also chosen each of these to be less than delta. So, okay, best case scenario, what we would do is we might have some period, right, where every single one of the bins has only one element in it. However, recall that this is less than delta. So since the spacing is less than delta, at least one of them has to include delta from that. So therefore, everything must actually end up having, or something must at least have two outcomes inside a single one. All right, great. So we know that 2 of them have to wrap around such that they're delta close to each other. Further, because consecutive elements are at least theta apart, because theta sub j minus theta sub k is less than or equal to j minus k theta mod 2 pi, I guess. This over here is less than or equal to theta because we're assuming j not equal to k. Okay? So that ends up saying that they have to be minimally that distance apart. And then from this, what that ends up saying is that as we repeat this process, you can't end up getting a sequence where what happens is all of these consecutive points that you end up getting to are closer and closer and closer, thereby getting outside of the preventing you from landing inside one of these delta windows. So every sequence that you take a look at with this property is ergodic, and therefore it will wrap around and densely fill the unit circle. Okay, so that is how that goes, and it follows from this and also the irrationality, because if it is rational, then there exists an n such that theta j equals there exists j not equal to k such that theta j is equal to theta k mod 2 pi. However, because we've assumed that they're irrational, this will never happen. Because they're at least theta apart, they can't clump, and so the only thing left is that they have to be able to uniformly fill the circle. And that's the idea. And so we just repeat this enough times until finally we end up getting 2 points that are going to be distance epsilon apart. Now, you can end up showing that if you've got 2 rotations, e to the negative I p theta, and then e to the negative I p theta, theta minus epsilon up here, the norm of that, this, using matrix norm properties, is less than or equal to sine theta minus sine theta minus epsilon plus cosine theta minus cosine theta minus epsilon. And then, using the fact that sine of x minus sine of y, absolute value, is less than or equal to absolute value of x minus y, and similarly for cosine, we end up getting to the fact that this has to be less than or equal to 2 epsilon. And so therefore, if we, by picking our epsilon to go to epsilon over 2, well, we guarantee that being epsilon far apart in angle ensures that the norm is epsilon small, and therefore it is always possible to be able to pick a sufficiently large value of n such that we're able to approximate the irrational rotation very closely. And that's the idea behind it. So now we know that we can actually build an arbitrary rotation. So now what I'm going to do is the next step, building a z rotation. Okay, so this, unfortunately, shows you that we can build e to the negative I p alpha for any alpha greater than 0 within epsilon for all epsilon greater than 0. Okay, so we can closely approximate any arbitrary rotation about the p-axis. What we want is we want to instead be able to make our z of alpha. Okay, so let's choose a let's take a look at what P is. Okay, so P is of the form ax plus by plus cz. We won't care, actually, really what these constants a, b, and c precisely are for this argument, because we can make any rotation angle we feel like. Turns out we won't need to worry about their precise value, but they can always be computed, obviously, for any individual thing that you're taking a look at. So say we want to be able to do this. Now, let's choose a very small rotation angle. Rp of epsilon equals e to the negative I p epsilon. This, by a Taylor series expansion, is 1 minus I p epsilon plus order epsilon squared. Okay, cool. So now this is, now let's consider doing the following. Let's consider looking at e to the negative I p epsilon over 2c. Then we'll do z e to the minus I p epsilon over 2c z. Okay, this, by using a Taylor series expansion, ends up giving us 1 minus I p epsilon from the first term times 1 minus I z p z epsilon plus order epsilon squared. And again, this epsilon is assumed to be small here. So now, what we can do is, using the fact that the above expression for P, we can use the fact that ZPZ is equal to negative AX negative BY plus CZ. And here I've used the fact that ZX, Z is equal to minus X, and Z equals minus Y. So by conjugating Z's around the P, we have flipped the signs. So when I expand this out, what I end up getting is I get identity. Oh, and I forgot, sorry, the over 2C over here and 2C there. We get identity minus I P plus ZPZ epsilon over 2c plus order epsilon squared. And again, remember, the product between those two is order epsilon squared, so we don't care about that to leading order. Now this is identity minus I AX plus BY plus CZ minus AX minus BY plus CZ times epsilon over 2c equals I minus I Z epsilon plus order epsilon squared equals e to the negative I Z epsilon plus order epsilon squared. And again, this epsilon we can pick to be any value we feel like. So for example, if we had a sequence of n gates, or n times we need to call this individual z rotation, then what it suffices to do, using the fact that u to the n minus v to the n is less than or equal to n epsilon, then we can end up picking epsilon goes to epsilon over n, and then we find that we can do e to the minus I Z n epsilon, and then the error from this argument is going to be at most n times epsilon over n squared equals e to the minus I Z n epsilon plus order epsilon squared over n. So by increasing this value of n, we can make this approximation error arbitrarily small and do any z rotation we feel like. Once we have the ability to do any z rotation with an arbitrarily small error, then we can end up doing RZ of gamma, Rx of beta, RZ of alpha, which again, this builds any one qubit unitary. All right, so any one qubit unitary can be built by that sequence. And so that is how we end up building single qubit rotations out of this. Okay? Final thing is that the previous universality proof that we discussed ended up using Toffoli gates. However, what we have now is we have H, T, and C naught rather than Toffoli. So how do you build it? Well, the easiest way to do this is just actually go through the following construction, which is given in Nielsen and Schwang. The construction is the following. Okay, and this is equal to controlled knot, it turns out. You can go through and evaluate that it does this for every step along the way. But something that you can, in order to be able to understand some of the logic behind this, there's one trick that I want to show you. And that trick is recognizing what happens when we end up having a C naught conjugated around a RZ gate. So the idea basically is, let's look at the following. Transformation, okay? Which is something that's kind of implicitly showing up here in particular, but also ends up motivating some of the logic behind why these C naught gates are popping up. This ends up having the property that, recall that Z or X, ZX is equal to minus Z. Therefore, e to the negative I Z theta with X's put around it is equal to e to the I Z theta. Therefore, we know that X, just by definition, XRZ of theta X is equal to RZ of minus theta. Or, in other words, it's RZ inverse of theta. Okay, so by putting X's around, we can end up controlling this, this rotation. So what this means is that if we have 0 and psi fed into this circuit, what we end up getting back out is, well, we just end up getting 0 and RZ acting on phi. However, if we put 1 and psi in there and stick it through the circuit, then what we end up getting out the other side is 1 and RZ inverse psi over here. So this allows you to controllably flip the direction of the rotation, i.e. flip a T over here into a T dagger. And so this gives you ways of selectively going through and causing, based on different Boolean logic for these inputs, the phases that you're applying to partially cancel out. So that's the reason why this circuit ends up kind of fitting into this particular form, but it's mostly an exercise in order to be able to show that this ends up yielding precisely the result that you're looking for. So that's more or less that. So TOEFL can be implemented using these, and therefore, because I showed that everything else can be implemented using just the straightforward logic, that we can implement all unitary transformations using this discrete gate set. All right, cool. So now that we've proven universality, we've shown that we can implement any arbitrary quantum transformation that we feel like. I mean, it might require exponential time, but in principle, we can do that. The next question is, all right, well, how do we end up extracting information from a quantum system? And so in order to be able to do this, we're going to take a step back and look again at measurement. And here I'm going to be introducing two ways that you can extract information out of your quantum system that are related, called the Hadamard and the swap test. And the lecture after this, I'm going to be talking about phase estimation, which is another related approach, widely used in quantum algorithms to estimate eigenvalues. So let D be a diagonal matrix. Okay, and now what we want to be able to do is we want to be able to talk about an expectation value of D. So for example, let's say we have the following situation. We've got 1 and 0. Okay, this is the example that I gave previously. This matrix counts whether input is 0 or not. Okay. Similarly, we could do this in higher dimensions. If we did this for 2 qubits, the analogous operation would be that. Okay. So what we can do is we can end up saying that, just like we did before, the probability of 0 for a given quantum state is equal to psi d psi in this particular case. However, if we end up writing psi as the sum over I square root pi e to the I theta I, then we can end up seeing that in general, psi d psi is equal to the sum over I pi dii. So what this ends up meaning is that for any arbitrary matrix over here, where we take a given set of values on the diagonal, we can end up seeing that this sandwiched result ends up forming the expectation value of all these diagonal elements. So for example, if I had, say, matrix 1, 2, 3, and 4, and I had a quantum state psi equals, I don't know, 1 over root 2, 0, 0, plus 1, 1. What I'd like to be able to do is I'd like to be able to figure out what the mean value of this is over here. So I would do the following protocol. I would measure psi. Okay, let's say that I get 0, 0 coming out of it. I look up the corresponding element, and I would say, okay, well, my function output will be 1. And let's say I end up getting psi goes to 1, 1. Well, then I'd look that up, and I would say my function value is equal to 4. Now, if I repeat this, the probability that f equals 1 is, well, 1/2. The probability that f equals 4 is 1/2. And therefore, the expected value of f is 1/2 times 1 plus 1/2 times 4 equals 2.5. Okay, so that's how we would find out the expected value of this function if we classically knew this diagonal over here based on all of these individual outcomes. Now, let's figure out how we could do this in one step quantum mechanically. In one step quantum mechanically, if we can perform the following, well, psi d psi, that in this case is just using our above expression, that ends up giving us 2.5 just the same. So in the event that we can implement d on a quantum computer, then we can compute this expectation value. Okay, well, that's great, but how would we do this? After all, d isn't unitary. Well, the first step is write d as a sum of unitaries. So, for example, let's say we want to do the matrix 1, 0, 0 over here. But that is equal to, again, this. This matrix we can actually write as 1/2 identity minus or plus poly z, which is equal to 1/2, just so you can visually see it, 1, 1 plus 1 minus 1. And you see that these two will cancel. Those two will add together to be 1. So we can write d as a sum of these unitaries. So the expectation value of d in some quantum state, which corresponds to the average value of this observable, or which is another word for this Hermitian matrix that we've got over here, is equal to, in general, 1/2 of psi plus psi z psi. And in this case, well, it's very simply just 1/2 plus the average value of this unitary operation over 2. But still, we don't necessarily know how to compute that. Now this over here is of the form psi u psi. Okay? So how can we end up doing this? Well, the Hadamard test gives us a way of doing this. And this is one of the most useful tricks in quantum computing. And so let me show you what the Hadamard test is. It's very, very straightforward. The Hadamard test ends up taking a form like this. You start with a quantum bit in 0. You perform a Hadamard transform on it. Then what you do is you apply a unitary. Then you apply another Hadamard transform and measure. Okay. My claim is that the probability of 0 is equal to 1/2 of 1 plus the real part of the expectation value of u over here. So by performing this circuit and measuring this result over and over and over again, you develop enough sample statistics in order to be able to approximate this expectation value, or at least the real part of this expectation value. So let's go through the analysis and see why that's the case. Oh, and this is psi down here. So we begin with our quantum state, 0 psi at input. First thing we do is we apply a Hadamard transform on the top quantum bit. We end up getting 0 psi coming out of it, and then 1 psi on the other branch. Now we perform a controlled unitary operation over here. This will only apply the unitary operation if the first qubit is 1. And so therefore this maps to 0 psi plus 1 u psi. Okay, now we've only got one step left. We Hadamard transform. This ends up giving us 1/2 0 psi plus u psi plus 1 psi minus u psi. And this minus sign over here is a consequence of the minus sign in the Hadamard transform. Okay, wonderful. So this is our circuit. So let's call this state over here phi. Now, I want to be able to figure out what the probability of 0 is. Well, the probability of 0, we can use this exact same indicator function trick that I was using earlier. If we go, and this indicator function trick basically ends up saying, okay, well, what we would like to do is we'd like to be able to figure out what this probability of 0 ends up being. So we want to be able to find a, let's see if I didn't introduce it yet. Okay, never mind. So what we'd like to be able to do is we would like to be able to find a quantity such that p of this function, what we'd like to be able to do is we'd like to be able to take in an arbitrary quantum state of the form, say, 0 chi over here. And we'd like to be able to map that to just the value 1. Similarly, if we have the state 1 chi for any state chi, we'd like to be able to map that to 0. So that's what this counting function does. It counts whether or not a portion of the quantum state is parallel to 0 in the first qubit or not. And it acts as 0 or 1. And the expectation value of f over here is clearly then the probability of 0. Now, the expectation value of f, we can end up implementing in the following way. We can say that f goes to the following operator. Okay, like this. So this is a projector onto 0. And this part over here is just the identity. It says, I don't care what we do to the rest of it. And then the way that we end up applying this to a given vector is we end up saying that f of 0 chi, let's call this p over here, is equal to 0 chi p 0 chi. Now, because p is equal to what it is, this is equal to 0, 0, tensor identity 0 chi. Okay, but using the properties of matrix multiplication across tensor products, we end up seeing that this is actually just 1 over here times the expectation value of identity in the state chi, which is equal to 1. All right, so this actually has the desired effect. Similarly, if we put in 1 over here, because of the fact that 1 is orthogonal to that projector, this will always be 0. So this is one way of doing it. And what we want to do is we want to be able to find the expectation value of this. So what we end up getting is, in general, for any quantum state, the probability of 0 can always be written as the expectation value of psi 0, 0 tensor identity psi over here. Okay. So that's how we end up doing that. And now that we've got that, we can actually use this substitution plus that form in order to be able to figure out what the probability of 0 is. So the probability of 0 in our case, substituting that back there, we end up getting 1/4 0 psi plus psi u dagger times 0 psi plus u psi. And here I've just used the fact that AB adjoint is equal to B adjoint A adjoint. And that's how I ended up getting this when I take the adjoint of the other terms. So computing this inner product, we end up getting that this is equal to 1/4 2 plus psi u dagger psi plus psi u psi. Okay, but this is actually equal to 1/4 of 2 plus psi u psi complex conjugate. Or I should say adjoint. I'm skipping a step here. Now, because this is a scalar, it's just the expectation value of an operator, this scalar adjoint is actually equal to 1/4 2 plus the complex conjugate of this. Okay, now note that if we have x plus I y in general is equal to some complex number z, then we have z plus z star is equal to x plus iy plus x minus iy is equal to 2x. And x, that's the real part of the complex number. So this we can write as twice the real part of x. So this whole thing is 1/2 1 plus the real part of psi u psi. Fantastic. And so the main thing that remains at this point is to argue, okay, well, if we want the full expectation value, then what about the imaginary part, right? Because this only gave us a way to figure out the real part of the expectation value of a unitary operation. So the imaginary part we can actually similarly find just by modifying the circuit slightly. So the way that we modify the circuit is we begin with the Hadamard transform, just as before. We apply a controlled unitary transformation down below. But now what we're going to do is we're going to end up putting in a S dagger gate. Hadamard. And recall that S dagger is equal to 1 minus I over here. And why did I do that? Well, if 1, then this gate does 1 goes to minus I 1, i.e. what it will end up doing is that it'll take the components that we end up having for u and then switch the real and the imaginary part, because x plus iy will end up going to minus iy, or minus ix plus y. So now the real part, after doing this transformation, now is actually the complex part of what we would have had before, or the imaginary part of what we would have had before. So this allows us to extract the imaginary. And with these two circuits, we can figure out both the real and the imaginary parts of any quantity. And this allows us, again, to compute expectation values or all sorts of things. In general, if we've got any matrix that we would like to be able to find this over here, we can always end up writing this matrix as a sum of unitaries. I mentioned this previously with a finite example, but it turns out that actually there's this expansion that you can end up doing in the poly basis, where we can end up writing this as sum over I, or as ax plus by plus cz plus d identity plus e prime xx plus a prime xy, b prime xy, plus so on and so forth. So we can end up building up a series like this and finding all of the coefficients to represent an arbitrary matrix in this over here. And the way that you would do this in practice, in case you're wondering, is we can end up finding the coefficients in this expansion through, a is equal to 1/2 trace of m against x, which ends up giving us an inner product relationship in this space. So this shows how you can end up building an arbitrary operator or matrix that you'd like to be able to take the expectation value of. And then by summing through all of these expectation values of different unitaries, you're capable of figuring out the average value of that on a quantum computer. So this is how we end up finding expectation values of arbitrary matrices on a quantum computer. And the next step that I'd like to do is I'd like to spend some time to talk about the swap test. So the swap test is another similarly useful circuit. And the idea basically is, assume that you've got a box over here, or two boxes, okay? And what they'll do is they'll feed out two different quantum states, psi and phi. And what we'd like to be able to do is we'd like to be able to compute the inner product between them squared. So we'd like to be able to figure out the overlap. And this measures how similar the states are. And actually, it can be used in order to bound the number of samples that you need in order to be able to discriminate between the two with high probability. So the swap test gives us a way of computing this value up here. And the circuit, which implements this over here, actually takes a very similar form. We start out with two copies of these states, psi over here and phi down there. Now, what we do is we perform a controlled swap operation. And again, recall from last time that a controlled swap can always be written as a Toffoli gate followed by two C-naughts. Okay, and what it does is it really just swaps this. So if we've got a state psi or phi over here, and this is 1, we'll end up getting psi up here and phi down there. All right, great. So my claim is when we do this and measure the top qubit, the probability of measuring this qubit to be 0 is equal to 1/2 of 1 plus the absolute value of psi phi squared. Okay, now this is actually also really important for quantum machine learning algorithms, because in many quantum machine learning algorithms, what we need to do is we need to be able to figure out the inner product between different vectors in order to be able to compute the distances between them. So this test is used extensively in some algorithms in that space. It's also used in quantum fingerprinting, as well as other cryptographic applications. So this is what we have. Now, let's go through and verify that this works. Okay, so first thing we do is we start with the state 0 psi phi over here. Now this, after applying a Hadamard transform, gives us 1 over root 2, 0 psi phi plus 1 psi phi. Now we're going to do next the controlled swap. On the first bit, because the input is 0, it doesn't do anything to it. So it'll just leave that as psi phi. However, it's 1 over here, so we are going to end up swapping. So in this case, we have phi psi coming back out. Great. Now, just like before, all we need to do is Hadamard transform again. And this Hadamard transform will end up giving us 0 psi phi plus the swapped bit from here, which is phi psi. And then we'll end up getting 1 psi phi minus phi psi. Okay, cool. And let's let this state be equal to chi. So the probability of measuring 0 on the top quantum bit, I'm going to explicitly write as chi 0, 0, tensor identity on this register, because we don't care about the value of psi over here for the purposes of computing a probability of 0. Similarly, we don't care about the state of the bottom one. So this probability is, this is chi over here, is that. Now we can see that because 0 is orthogonal to 1, we can drop that part from both sides of the equation. And this ends up giving us 1/4. And we can actually even drop the 0, because we know that's going to have a trivial inner product of 1 over here. So this probability is going to be psi phi plus phi psi inner producted with psi phi plus phi psi. Now, distributing this inner product, we end up getting 1/4, 2 plus psi phi phi psi squared. Oh, sorry. No, that is plus 2 of those. Okay. Now, first thing to note is using the fact that this is a scalar and using the fact that AB transpose is equal to B conjugate transpose A conjugate transpose. We can end up seeing that psi phi dagger is equal to, because it's a scalar, psi phi complex conjugate, but that is equal to phi psi. So we can replace this with that. And so this is equal to 1/4, which I'll replace with 1/2, 1 plus absolute value of psi phi squared. Because for any constant, A is equal to absolute value of A squared, or is defined to be equal to that. Okay, and so this gives you a way of computing the inner products between two vectors. So that is the Hadamard and the swap test in a nutshell. And they give you two ways of extracting information from a quantum system. So one thing before proceeding, next lecture, we're going to spend some time talking about the phase estimation algorithm, which is a very similar circuit, but its analysis is a little bit more complicated. But I'd like to be able to give some intuition, because one thing that you'll note is that both of these algorithms end up taking a form like this, where we have a qubit at the top, we apply a Hadamard transform, we do something, we then Hadamard transform again, and go back. The reason you might ask, okay, well, why? What's happening with this? Well, what we're doing over here, when we create a Hadamard transform, when we apply a Hadamard transform to this over here, we can envision this bit as keeping track of which path computationally we're going through. Okay? So, for example, in the case where we had a controlled unitary, what we're doing is our execution ends up breaking into two possibilities. We have 0 down here, and we have the 1 branch up here. In the event that it's 1, then we apply the unitary. If it's not, then we don't. Now, what we do at this point is we kind of merge them back together. And the phases that we end up getting from both of these paths that the program could go through, they interfere at this point. And that's the purpose of the Hadamards. The Hadamards cause the split, which causes the path to break into two components. And then the Hadamard, again at the end, forces the two to merge once more. And the probability of getting, 0 or 1 coming back out is given by the degree of interference that we end up getting. The similar sort of thing ends up happening if we have a controlled swap operation inside here. We again now are comparing the case where we're swapping the two states. In the event that they're exactly the same, well, the circuit, you can see for the swap test, will do absolutely nothing, right? Because if we have two copies of phi, we have psi, and swapping, well, we'll just give you psi again. So in that case, this circuit really boils down to nothing, which is, and the difference between the two really ends up coming about only from to the extent to which these two states are different. So you can intuitively understand why this circuit is doing what it's doing just by understanding that swap will happen to take two copies of exactly the same state back to itself. And we're using these two branches over here to create a reference. This reference where nothing happens, and we compare it up against the path where it does happen. And by looking at the interference between these, we can infer what the action was. So this, at a high level, is how the swap and the Hadamard tests end up working. Next lecture, we're going to go into some more detail talking about how phase estimation works, and then after that, we're going to be touching on quantum algorithms. In particular, we're going to be going into quantum query complexity. All right, well, thank you very much, and yeah, I'll see you all next time.